तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome to another session in database management systems. We have covered quite a bit of ground in the explorations of DBMS already. We have looked into logical models of data management from the conceptual perspective, from the physical perspective and so on, and we also looked at physical requirements of data storage, although we have only looked at very specific kinds of physical data storage and retrieval strategies for databases. We also looked at a few kinds of index structures over which or using which we can efficiently access or efficiently search and retrieve for the relevant tuple or the relevant record that we are looking for in a database management system. Usually when we are talking about databases, there is sometimes a philosophical question that is raised as to whether any collection of data is a database, especially perhaps in the late 90s there was this raging debate about whether the web, the World Wide Web is just a large database. Now of course one might be tempted to believe that any collection of data is a database, some would argue that no, that is not really true. Collection of data is just a collection of data. It's something like the difference between a set, a bag and a relation and so on. All of them are just collections of some things. A set of tuples or a bag of tuples or a relation of tuples, all of them are just a collection of tuples. However, some of them, for example sets or bags, impose what are called as additional constraints over this collection. A bag of tuple is simply a collection of tuples, and there is no constraint whatsoever on what should be the tuple, what kinds of tuples should be there, what should be the size of each tuples, what should go into what should define the attributes that make up the tuples, and what about duplicates in the tuples, how many different kinds of the same, how many different numbers of the same kinds of tuples can be there and so on. There are absolutely no kinds of constraints that are imposed on a bag of tuples. However, when we consider a set of tuples, there is an implicit constraint that is imposed, that a set is a collection of things of the same kind, although not always so, but usually we talk about a set as a collection of things of the same kind. Therefore, when we say a set of tuples, we tend to believe that it is a collection of things or collection of tuples of the same kind, that is, all of the tuples have the same number of attributes, and each attribute or each corresponding attribute of each tuple has the same domain and so on. And there is also an implicit constraint that there are no repetitions in sets, that is, two or more tuples cannot have the same value for every corresponding attribute that they contain. Therefore, there is an implicit constraint of no duplicates that is imposed on a set of tuples, and of course in order to implement this, that is, in order to implement a bag of tuples and to implement a set of tuples, the kinds of programming that we have to do, the kinds of logical checks that we have to do changes. Implementing a bag of tuples is the easiest. We just maintain one collection of tuples using whatever data structure that we can use for maintaining collections, linked lists, trees, whatever, arrays and so on. Similarly, in order to implement a set of tuples, we can use the same kind of data structure in order to implement a collection. However, we have to keep making checks so that the set property of this tuples are maintained. That is, we have to maintain checks that all of the tuples are of the same kind and there are no duplicates that are there in the tuples. Moving on, if we consider a relation of tuples, a relation of tuples is also a collection of tuples just like a bag or a set. However, it imposes even more constraints on the set of the set of tuples. That is, we have seen some kinds of relational constraints like the entity constraint, the key constraints, and referential constraints, no duplicates, and so on. So a relation also does not allow for duplicates in tuples. It also explicitly states that all tuples have to be of the same kind. That is, they have to adhere to the same schema that is defined by the relation, and it explicitly forbids any tuple that does not adhere to the schema, and there are strong constraints of about how the values of each attribute should be, that is what should be the domains, and how each what is the domain of each attribute, and where can a value lie, and so on. And there are other constraints like key constraints which can uniquely define a tuple, and because there are no repetitions in a relation, by default the set of all attributes of a tuple form its super key, and so on and so forth. In this session we are going to look at these constraints in much more detail. We are going to be concentrating on the concept of constraints and an associated concept of triggers in database systems. Triggers are a concept that are quite prevalent in what are called as active database systems, and we are going to be looking at triggers in this context in this session. So let us look at what are the different kinds of constraints that are imposed either implicitly or explicitly in a typical database management system. Let us define the term integrity constraints. As the term implies, integrity constraints are constraints that strive to enforce the integrity of the database system. What is an integrity of a database system? The integrity of a database system or a system of data elements essentially states that the set of all data elements that are stored in this system is a valid set. Note that valid set or validity is different from correctness. Validity simply states that validity is some kind of correctness that is independent of what the user or what the application really considers semantically correct from the usage perspective. For example, if I state that the marks obtained by a student can range from 0 to 100, then a value of 200 for the attribute called marks is an invalid number. It is not at all. It is not valid. So this pertains to validity. However, if I enter a value called, let us say, 50 for a particular student, it may be valid. However, it need not be correct. It could be an incorrect entry for that field. The student may have actually obtained 90 marks, whereas I would have entered 50 for the student. Therefore, it is an incorrect value. However, it is a valid value. Integrity constraints as part of the DBMS are independent of the application programs. They have no idea about what is the application context or what is the usage scenario in which this particular data element is being used. Therefore, they can only talk about, or they can only enforce validity of the database values or of the data elements stored in the database. They cannot obviously ensure correctness of the data that is stored in the database. One of the first form of key constraints in the relational model, one of the first form of constraints in the relational model is the key constraints. We have seen key constraints when we talked about the relational model and also in SQL, but let us revisit key constraints here again for the sake of completeness when we are talking about constraints. Key constraints is a very fundamental form of relational constraint, and it manages entity existence and of referential integrity. What is meant by entity existence? Entity existence essentially means that we should be able to dereference, that is, we should be able to identify each entity or each tuple in our database uniquely. So that essentially means that each entity should have at least one super key using which it can be uniquely identified, or it can be uniquely distinguished from the rest of the tuples in the database. In the relational model or in the relational algebra, since a relation forbids duplicate tuples, the entire tuple in the worst case itself is the super key of the tuple. So the key constraint therefore states that key attributes should be unique across the relation, that is there should be no two tuples having the same key attribute, that is if I identify a subset of attributes as the key attributes, there should be no two tuples such that the key attributes are the same, that is such that they are indistinguishable as far as the key attribute is concerned. The entity constraint stipulates that the key attribute can never be null, because all null attributes are the same no matter where they occur, and there is no difference between a null attribute in the name field versus a null attribute in the age field. All null attributes are the same. That means it means that there is no value associated with it. The entity constraint therefore states that the primary key relation, that is the relation, the subset of attributes that can uniquely identify tuples in a relation, may never be null. And the third kind of key constraint is the referential integrity constraint. The referential integrity constraint essentially is a constraint over the foreign keys. Remember what a foreign key is. A foreign key is a set of attributes or a subset of attributes within a tuple that refer to another tuple in a different relation. Mainly the primary key or any key attribute of another tuple in a different relation. A foreign key or the referential integrity constraint states that a foreign key should either be null, that is it should not refer to any other tuple, or if it refers, that is if it is not null, then it should refer to an existing tuple. We cannot refer to a tuple that does not exist. We cannot assign a manager to a department, for example, which is non-existent. We cannot assign a manager to a non-existent department. On the other hand, we can say that a manager is not assigned to any department at all, that is set the foreign key as null, which is quite acceptable as far as the referential integrity constraint is concerned. How do we specify key constraints using SQL? We have seen this in the session on SQL. Let us briefly summarize it here again. Note the creation of a table in SQL. The following slide shows a table called employee, which has two key constraints. One is the employee number, which is the primary key, which is marked as a primary key, and there is a PAN number for each employee, which is a secondary key. That is, it is given some constraints called non-null and unique and so on. And there is also a foreign key, that is the field called reports to, which states who is the supervisor or who is the manager to which this employee reports to. So the foreign key references another employee tuple and references the field called, or references the attribute called employee number in another employee tuple, or in another employee of another tuple in the employee relation. So this is these are the circles that are shown in this slide depict how the key constraints are identified. The first circle shows that when we stipulate that PAN number is not null, then we have identified that as a key constraint. That is, it is one of the keys by which can uniquely identify tuples in this relation. The second circle shows that the employee number is primary key, is a primary key, which implicitly states that employee number may not be null. So therefore the not null constraint in the for the employee number is actually spurious, but nevertheless it states that employee number is another key which is used as the primary key, that is, which is used to which is actually used to dereference every tuple in this relation. Finally, we have we identify foreign keys using the foreign key construct, that is, we identify which first of all which field in this tuple is the foreign key, and it refers to which field in which other relation, that is, it references the relation called employee and the field called, or the attribute called, employee number. How can key constraints be enforced? Now that we have seen some physical aspects of data storage or data management, let us go inside the DBMS to see how or what could be a possible means by which constraints or key constraints can be enforced. A simple way of enforcing constraints is to create an index structure over the field that form the keys. For example, if we create any kind of index structure, let us say primary index on the declared primary key attribute, then we can easily enforce the unique constraint. Note that primary key has to be unique, all keys have to be unique. Therefore, whenever a new tuple is being inserted into the database system, we just use the index structure to verify whether a key attribute of this value already exists in the database system or not. If it already exists, then inserting a new tuple with the same value is going to violate the uniqueness constraint, so in which case this can be rejected and the integrity constraint can be enforced. Similarly, for all other attributes, that is all secondary key attributes, we can maintain secondary key indexes such that we can always verify whether before insertion of a tuple whether the corresponding value for that key actually exists in the database or not. Referential integrity similarly can be verified by using a primary index over the other table, that is over the table that is being referenced. Therefore, whenever I insert a tuple in a relation that contains a foreign key, I first verify whether this tuple in fact really exists in the other table, whether the foreign key references to a tuple that actually exists in the reference table. Only if this is so, then I would allow the insertion of the tuple in the referencing table. So let us probe a little further into enforcing referential integrity. In SQL, SQL automatically rejects whenever a tuple is being inserted into a relation containing a foreign key such that the foreign key is not null and it refers to a non-existent tuple, and this rejection is performed using corresponding index structures. And by default, SQL uses the restrict option for managing alterations or updates in tables. For example, if a tuple is deleted, or if a tuple is asked to be deleted in the referenced table, that is, let us take an example of a manager working in a department. If the department tuple of the corresponding department table is to be deleted, then SQL rejects such a deletion because there is a foreign key constraint, that is from the table called manager, which is referencing this tuple, unless of course we use the cascade option, in which case even the corresponding referencing tuple would be deleted, that is the corresponding manager tuple which is referencing the department tuple would also be deleted when the department is deleted. Similarly, SQL rejects any updates to the part to tuples that can affect the foreign key constraints. For example, if I try to update the department ID in the manager table such that it now points to a non-existent department, SQL rejects this update. On the other hand, if I try to update the department table and change the department number such that it violates some foreign key constraints that are pointing to it, that is it makes some foreign keys dangling, then SQL would reject such an update. Of course, updates and deletes can we can force the DBMS to go ahead with the updates and deletes by using the cascade option, in which case the overall referential integrity is still maintained. However, updates and deletes are cascaded, that is every referencing tuple is also updated whenever the reference tuple is being updated. There are also other constructs in SQL that instructs the DBMS to perform in a different fashion, to act in a different fashion than mere cascade. A cascade simply says that whatever changes is being made in the reference tuple, make the corresponding changes in the referencing tuple. That is, if I change my department ID from 50 to 102, change all referencing tuples that are referencing to department number 50 to department number 102. That is simple cascade. However, we may want to do some other operations other than simple cascade. There are other options that we can use to instruct the DBMS to perform differently. One of such options is the set null option. Have a look at the relation shown in the slide here. The slide creates, or the relation creates a table called employee, where employee number is the primary key, and there is a field called name, and there is a foreign key called reports to, which is the employee number of the manager or the other employee to which this particular employee reports to. Therefore, foreign key references employee relation and the employee number field, and then in the foreign key relation or in the foreign key specification, there are two other constructs. The first construct says that on delete set null, and then the second relation says or the second construct says that on update cascade. What do these things mean? The first thing, the first construct says that on delete set null. Essentially, it means that if the tuple that I am referencing to is deleted, then set null. That is, set this field to be null. Note that a foreign key can be null without violating referential integrity. Therefore, the semantics of this statement means that if the person whom I am reporting to is for some reason deleted from the set of employees, then set the field as null, that is, I am not reporting to anyone. On the other hand, if the person to whom I am reporting to changes his employee number, let us say I am reporting to a manager with employee number 102, and the employee number is changed to 150, then it says on update cascade, that is, cascade this new employee number to and make corresponding modifications in the foreign key construct so that referential integrity is maintained. SQL also supports what are called as deferred constraint checks. A deferred constraint check essentially says or tells the DBMS that when inserting a tuple that don't make a constraint check right now. Why do we require a deferred constraint checks? Deferred constraint checks are especially useful when we have circular constraints or circular referential integrity. Have a look at the figure shown in the slide here. The figure shows two tables with corresponding referential integrity. The table essentially states that the first table is a manager table which contains a primary key called employee number and the name of the manager and the department ID that is managed by the manager. The department ID field is a foreign key into the department relation. The department relation in turn is having a primary key called department ID, it has a department name and a field called manager, which in turn is a foreign key onto the employee number. Consider that this company which is having a schema like this has recently upgraded its database system, and now they have installed a new DBMS, and they are now porting the set of all data that they have from their old database system to the new database system. Now when they are porting, which essentially means that they are adding these tuples in a batch mode, adding a set of tuples in a batch mode, there is no guarantee that, or it is very difficult to guarantee that the tuples would be added in the order in which they are required. That is, whenever I am adding a department ID, the employee, the corresponding employee ID for the manager already exists, and whenever I am adding a manager tuple, the corresponding department ID for which he is a manager already exists. This is very difficult, if not impossible, to sustain or maintain. So in such situations it is useful to have a deferred integrity check. So if we use the deferred or deferrable option in SQL, then the DBMS defers integrity checks till the present transaction is completed. We have not looked into the concept of transaction as yet. However, let me give a brief intuition about the notion of transaction. A transaction simply is a logical unit of database operations. For example, if I talk about debiting and crediting between two accounts, let us say I am performing a wire transfer between my account and my friend's account. So a transaction in this case is the set of operations that debits a set of an amount of money from my account and credits it to my friend's account. This entire set of operations belongs to one semantic entity or semantic transaction, so to say. So and either both of them have to be performed or none of them should be performed. That is, either both debit and credit should happen or none of them should happen. It shouldn't be the case that my account is debited but my friend's account is not credited, or the case that my friend's account is credited with some money from somewhere but my account is not debited. Either both of them should be should happen or none of them should happen. So the deferrable option essentially defers integrity constraints, that is until the end of the transaction. In the middle of a transaction we might encounter a situation where the integrity is violated. However, that is okay as far as we have at the end of the transaction we have perfect integrity, that is we have maintained the integrity of the overall database system. This slide shows how or what is the syntax of the deferrable construct. Have a look at the slide here. The slide creates a table called manager, which is shown in the previous slide, or which was shown in the previous slide, and manager has an employee number attribute which is a primary key, and a name attribute and a department ID which is the foreign key. And of course there is no need to separately specify a foreign key if we directly say that department ID references some other tuple, that is department ID, and we say that it is deferrable and also that initially deferred, that is it is initially deferred. That means to say that deferrable essentially means that it is possible or it is okay if integrity check on this referential integrity is deferred till the end of the transaction. And the second one says that initially deferred means explicitly tells the DBMS engine that as soon as a tuple is tuple of type manager is inserted, initially defer the referential integrity checks. Let us move on to other kinds of constraints from key constraints. The next kind of constraints that we are going to look at are constraints on attributes. Of course we have already seen a few constraints on attributes, as some examples are shown in the slide here. The first constraint that we have seen was the not null constraint, which essentially states that null value for this particular attribute is not a valid value. And the second kind of constraint, which is also a key constraint but some sense also a attribute constraint, is the unique constraint. It essentially checks against duplicate values of the attribute being inserted into the relation. A more general form of attribute constraints in SQL is what is called as the check option. We can specify any general kind of attribute constraints using the check option on a relation. There is an example, or there are two examples shown in this slide here. The first example defines a field or an attribute called gender and says that it comprises of a single character, char1, and then imposes an integrity check on the value of this field or the value of this attribute. It says that check gender in M or F, that is, those are the only two valid characters that can be assigned for gender. Even though it is a single character, it is not just a single character, but it is a single character in this set of two characters M and F. Similarly, the second example shows a field called age that contains an integer of 2 digits, which can contain an integer having 2 digits, and there is a check that states that check that age is greater than 18, especially if we are talking about employee records and so on. There might be a legal integrity constraint, that is a legal minimum age for an employee of 18 years, therefore that can be directly included as part of the check constraint, that is check age greater than 18. Note that the first constraint, that is check gender in M or F, is a physical constraint, that is it is a constraint that is given as part of the physical world around us. And the second kind of check that is used, that is check age greater than 18, is a normative constraint. It is a constraint that is imposed by the local laws or the set of norms which define the set of correct behavior within this system, and it can change from system to system. In some places probably the minimum working age is let us say 16, or in some other places it could be 21 and so on. So that is a normative constraint, while the former constraint is a physical constraint. We now ask a sort of interesting question: can the attribute constraint, that is can the check constraint on values of attributes be used to enforce referential integrity? Referential integrity, as you know, is a key constraint, that is it is a integrity constraint across different relations. However, have a look at the small declaration here, which might seem to say that we can actually use a check as a check for enforcing referential integrity. The example shows that shows the declaration of a field called department ID, and department ID is shown as integer having 6 digits, and then there is a check here. The check says that check department ID in select department ID from department. Now this is the department ID of the manager tuple, and when a manager tuple is being inserted, there is a check that is made to see that the department ID that is being inserted for the manager actually exists in the department relation, which looks like, or which seems to suggest that we can enforce referential integrity using a check statement. That is, if we try to insert a tuple, or if we try to insert or even modify a tuple of the manager relation such that it tries to reference to a non-existent department ID, this check fails and the updates or insertion is rejected, which seems to suggest that referential integrity can be enforced using check. However, look at the other way around. What happens if a department existed when the manager tuple was inserted, and then at a later point in time the corresponding department tuple was deleted. There is no way that this check constraint is now enforced, because the check does not even know that the corresponding tuple from that is being referenced in the department table is being deleted. Therefore, because of this, because such situations cannot be handled by check, we say that we cannot use the check condition for enforcing referential integrity. The check constraint can not only be used on just an attribute basis, it can be used on a tuple wide basis. That means a check constraint can actually perform checks on several attributes on a given tuple. The following example shows such a situation, where it says age int of 2, that is the age of an employee, let us say, is declared as an integer having 2 digits, and a check is performed to see whether age is greater than 18, that is the legal age for a particular employee in a given company setting should be greater than 18, or there could be children employed by the company as long as the job type is based on talent, that is job type is based on encouraging the child's talent. Therefore, you can either perform a check on the age field which says age should be greater than 18, or if age is not greater than 18, you can check a separate field or a separate attribute called job type to see whether it is set as talent in this particular tuple. It is possible to give names to constraints that we declare in SQL, so that they can be referenced by their names rather than by their actual conditions. This particular slide shows such an example, where the check called the legal age of an employee or the minimum age of an employee, the constraint on this is given a name called legal employee, that is age int of 2, and a name is given called legal employee, which is the constraint called check age greater than 18 or job type equal to talent. Once we have named tuples, we can alter constraints, that is once we have named constraints, we can alter constraints, that is we can add or delete constraints by referring to them by their names. For example, the following slide shows two different alter commands. The first command says that alter table employee drop constraint legal employee. If the particular constraint is no longer valid, we can refer to a constraint by name and then say drop it. So that constraint is no longer enforced in future additions of or future updates to the table. Similarly, the second alter statement shows how a new named constraint can be added to the table at any later point in time. That is, alter table manager and add constraint all works, that is the constraint name is called all works, and check that department ID is not null. That is check to see that for all the employee manager tuples in this manager relation, the department ID, that is the corresponding department which they have to manage, is not null. That is, there is no such manager who is not managing a department. Now what happens if there are already some fields or already some tuples in the relation whose department IDs are null? In such a case, the addition of this constraint fails. That is, the constraint cannot be added because it cannot be enforced on this table, because there are already some managers whose department IDs are null. A more powerful kind of constraint in SQL is are what are called as schema level constraints. Until now we have been looking at constraints that acted at the tuple level or at the key level, tuple or attribute or keys or so on, that is which acted on specific instances of a relation. A schema level constraint on the other hand acts at the level of a schema, that is which is enforced for all tuples or on a database wide basis. One such powerful constraint, a powerful general purpose constraint is what is called as assertions. Assertions are general purpose checks that can be performed on the entire database and can be enforced on the entire database for the entire time in which a database is in operation. That is, if I make a specific assertion, the assertion must be true when it is made, otherwise the assertion fails, of course, and the assertion must be true when it is made, and it must be true throughout the lifetime of the database or until the assertion is dropped. That is, once an assertion is made, it will be enforced. That is, every modifications to the database in whatever table, in whatever tuple would be checked to see that the particular or the specific assertion is not being violated. This slide shows an example of an assertion. An assertion can be created using the create assertion command. This slide shows a create assertion command that creates an assertion called no bench. No bench is the name of an assertion, and the assertion essentially checks, that is, an assertion is a check statement which checks to see that there does not exist any manager whose department ID is null. That is, there is no manager who is on the bench, so to say. That means who is not assigned any department to manage. And this assertion should be true when this is first asserted. That is, when I execute the create assertion statement, all managers in the database that are listed in the database should be associated with a department, and if there are any managers who are not associated with a department, then the create assertion fails. The assertion can be created only when either the managers who are not assigned any departments are modified to assign departments, or those tuples are deleted from the database. And once an assertion is created, that is, once such an assertion is created, it is enforced or it is maintained whenever there is a database update that is happened, and any update or any addition of a manager tuple whose department ID is null is rejected. And this set of assertions holds for the lifetime of the database or until the assertion is dropped or until the assertion is deleted. Assertions can be dropped using the drop assertion command. So we just say drop assertion no bench, and then the assertion no longer holds, and further on tuples violating this assertion can be inserted into the database. The second kind of schema level constraints that we are going to look at are what are called as ECA rules or triggers. An ECA rule expands to an event condition action rule. This is an integral part of specific kinds of databases called active databases. However, ECA rules have been incorporated into most commercial databases as of now. That is, let us say IBM DB2 or Oracle 9i or 10G, which is the latest. All of them incorporate some form of ECA rules. An ECA rule or a trigger is again a database wide constraint, but which differs from an assertion in the sense that they are not always active, that is, they are not always enforced. An ECA rule is enforced or an ECA rule is awakened only when certain specified events occur. That is, note that ECA stands for event, condition and action. So when an event occurs, a corresponding ECA rule is awakened. The rule then performs the rule then performs a condition check to check whether the condition hold. That is, when the event occurs, if the condition holds, then the rule performs a given set of actions. That is the A part in the ECA rule, and the action could be anything. it could be like preventing the event from proceeding, or undoing the event, or any other set of database update operations that could be totally unrelated to the event. It could actually be something like intimating the user about the event and so on. And the action in turn may generate more events, which in turn could trigger more ECA rules and so on. There are several options that SQL provides to handle ECA rules. We can either specify that the action part of a ECA rule be executed either before the event occurs or after the event occurs. That is, before a particular event is going to happen, make a check for any ECA rule that is waiting on this event, or one could check for performing the action after the event occurs. The action part of an ECA rule can refer to both old and new values of data elements that are modified by the event. That is, SQL or several or most commercial DBMS systems would maintain the older values of data elements that were modified by certain update events in case they trigger certain ECA rules, and the ECA rule would want to refer to the older value of the data element. For example, one might specify an ECA rule that says alert the user whenever the current stock price, let us say, falls below or falls by greater than 5%. Therefore, we need to know the older and newer value of this particular stock price in order to see whether the change in one update is greater than 5%. If that is so, then the user is alerted. And the action part of an ECA rule can be either specified to be performed once for each modified tuple, or once for all tuples that are modified during the update event, that is during the database operation. This slide shows a particular example of an ECA rule. It says all the keywords are shown here in a highlighted form. The keyword to specify an ECA rule is the term called create trigger. So this statement creates a trigger called overdraft, which has to be performed after update. That is, the action part of this trigger has to be performed after the update. Note that actions could be performed either before or after the update. So this has to be performed after update on a relation called prepaid, and referencing each new row, that is the new row that were modified as n row, and for each row that was modified, it checks whenever, that is when balance, that is nrow dot balance attribute is less than or equal to 0, then update update that row and set the attribute blocked equal to true. That is, for every prepaid account whose balance is less than or equal to 0, the account is automatically marked as blocked as part of this trigger operation. What are some of the properties of ECA rules? ECA rules are automatically triggered by the DBMS. The application program need not even be aware of the corresponding ECA rules that were triggered. It is the rule writer's responsibility, that is whoever enforces these rules, or whoever wrote these rules to enforce this integrity constraint, it is the rule writer's responsibility to ensure that the rules terminate. And it is also the rule writer's responsibility to prevent cascading triggers. That is, this action would in turn create another cascading action, which in turn would trigger some more rules, which in turn would create another cascading action triggering more rules and so on. So it is a rule writer's responsibility to prevent such conditions from happening. A rule writer can also write a cyclic rule, that is rule A triggers rule B, and the action of rule B triggers rule A. That is, rule A tries to undo something, undo an update, and which in turn triggers rule B, which tries to redo it back, and it can obviously go off into infinite loops. In most DBMS systems, termination and infinite cycles are simply handled by seeing or just maintaining a count of the nesting level, that is how many iterations have been made, and if this crosses a maximum threshold, then the entire set of operations including the update that triggered this infinite rules are rolled back, that is they are all undone, and nothing is changed, and the database state is taken back to the state before the event that created this infinite looping of rules. The last kind of integrity checks that we are going to be looking at in an SQL based database system are the notion of authorization and privileges. Authorization and privileges talk about which user is authorized to do what, or which user enjoys what kind of privileges. Users in an SQL based system can enjoy certain privileges that grants them certain authorizations. What do we mean by authorizations? And this could mean an authorization to read a particular tuple, for example. Is a particular or is a given user authorized to let us say look at the account details of some other user, or is a given employee authorized to look at the salary details of some other employee, and so on. Okay. So there could be a read authorization, there could be an insert authorization, that is a user allowed to insert tuples into the database. There is an update authorization, delete authorization, index authorization, that is index essentially means that can a user be allowed to create and delete indexes on a particular table. Why is this a security constraint? Why is index important? That is, why should a user be authorized to create and delete indexes? This is because what happens if a user whether intentionally or unintentionally deletes the primary key or the primary index structure on a tuple, then the entire database or the entire data file becomes extremely inefficient to access. Therefore, a user should be authorized to create or delete indexes. Then alteration and drop authorizations. What about views? What kinds of authorizations can we impose on views? Most database systems allow authorizations to be specified on views without obtaining the specific authorizations on the base table. That is, let us say a HR manager would have a read authorization on a HR based view of the employee records, that is which contains employee salary details, perks, and so on. However, there may not be or the manager may not enjoy read authorization on the actual employee tuple, which may contain some more information like his or her personal details and so on, which the manager may not be authorized to access. Therefore, even if the corresponding authorization does not exist on the base table, it is possible to obtain certain authorizations on the view. And since views are derived tables, whenever a query is given through a view, authorization checks should be performed before the query is answered. The general form of providing authorizations is to use the grant command. The grant command simply says that grant privilege list on a particular relation or view name to a set of users. This slide shows such an example which says grant insert, update, and select privileges on the manager table to public. Public means that all users, that is everybody, every user in the database system. The privilege names used in the grant command are the same names as the SQL command that is used for these privileges. That is, a select privilege gives an authorization for reads, an insert privilege gives an authorization for inserts, and so on. An update privilege gives an authorization for modifications, and so on. And all privileges, the keyword called all privileges, suppose we say grant all privileges, it means all the above privileges can be granted to the specific user in question. It is possible to revoke privileges, that is by using the revoke command, that is revoke privilege list on relation or view name from user list, and of course we can use the now familiar terms called either restrict or cascade. Restrict basically means that if I revoke a particular privilege from a set of from a given user, all the privileges that were granted by the user to other users will not be revoked, they stay in place. On the other hand, a cascade privilege says that if I revoke privilege X from a user, and if that privilege X has been passed on or granted by the user to other users, they are also invoked in a cascading fashion. So that brings us to the end of this session, where we have looked into the notion of constraints in the database system. Essentially, we have seen in different kinds of constraints that a typical DBMS system provides, and they can be classified as either key constraints that act on the key attributes of a particular relation, or they could be attribute constraints which can act on any attribute which checks domains or validity of the attribute value with reference to its domain in any given relation. And there are tuple constraints which act on the complete tuple itself, that is where the value of certain attribute may depend on the value of other attributes on a tuple wide basis, and so on. And then there are schema level constraints, especially assertions, which are a general purpose schema level constraint which maintain certain integrity over the entire database for the lifetime of the database, or until the assertions are dropped. And finally, we looked at triggers or ECA rules that are not valid always, but are awakened whenever certain events happen and a certain condition holds, and which in turn prompts them to perform certain actions. We finally then looked into the notion of privileges and authorizations that different users in a database system can hold, and they could be granted certain privileges, and privileges could be revoked from them, and this can happen in a restricted fashion or in a cascading fashion. So that brings us to the end of this session.